to start this part of our semester, I think it's important to explicitly say what I mean by ideal batch reactors. I know that wasn't really spelled out clearly in the first lecture. And when we're talking about an ideal batch reactor, we're really just saying that it is well mixed. And that means that there are absolutely no thermal or compositional gradients. Maybe if I was going to say that in English, it would be that the temperature and concentrations are exactly the same everywhere, okay, inside of the reactor. And with that in mind, let's move forward with our examples. I really like teaching by example, and we do the math that's going to be required in the context of the examples that we need to solve, as opposed to just doing a lot of math that you don't know why you're ever going to use it, okay? And so to do that, let's bring up our first example that we are going to solve. And to do that, we're going to consider an ideal batch reactor, right? No thermal or compositional gradient, where we have the easiest possible reaction that we could consider, and that is A goes to B. And you're going to notice that throughout the semester, A goes to B is going to be a really nice test case. It's an isomerization that's really, really easy to track. And we're given our reaction rate constant in this problem. And here, I'll make this slightly bigger so you guys could see it easier at first. And we know that the reaction rate constant is equal to 0.1 inverse seconds. We know that the volume of our reactor is 10 liters. We know that the initial concentration of A is 0 molar. And we know that the concentration of, is 1 molar. And we know that the concentration of B is 0 molar, okay? So the thing that we need to do now is apply our mole balance equations to A and B. And if you remember, our mole balance equation is simply that Fi in minus Fi out plus Ri times V is equal to dNi dt. And for a batch reactor, right, there's no flow. And now what we have to do is to come up with rate laws for A and B. And so here, A is being consumed. So the rate law for A is just equal to minus K1 times Ca, right? If this is an elementary reaction. And from here, we can actually insert this directly into our rate law and find, or into our mole balance, and get that dNA dt is equal to minus K1 times Ca times the volume. Now, we can't directly integrate this because we have moles here and concentration here. And we know that concentration is just moles per volume, okay? And we have a choice when we solve a problem like this. Do we actually want the solution in terms of moles, or do we want the solution in terms of concentration? So in this case, I'm going to solve this in terms of concentration. And we know that the concentration of A is equal to the moles of A over volume, right? And so we can make that substitution. And if I do that, and I want to get this in terms of concentration, I'm just going to divide this equation by volume. And so I can get dNA over V dt is equal to minus K1 times Ca. And the reason that I wrote it like this, and I didn't just explicitly put concentration at the beginning, is that we have to make sure that one thing is true to make the math easier. Is the volume constant, or is the volume changing? And that will dictate the math from here on out. So this is our first example. And a lot of times reactors are built anyway with a constant volume. So let's keep the math relatively simple to just sort of demonstrate the principles that we're trying to learn. And so we're going to say that we have a constant volume in this particular reactor. So that means that we can make this substitution. And now we have dCA dt is equal to minus K1 times CA. Okay. And we know that at time equal to 0, CA is equal to, we'll just call it CA0. So we can get a really nice, easy functional form to solve. Now, if you remember, solving this from differential equations, right, this becomes dCA over CA is equal to minus K1 times dt. And we're going to integrate this from CA0 to CA. And we're going to integrate this from 0 to sometime in the future, t. And if we do that, right, this just becomes the natural log of CA evaluated from CA0 to CA equals minus K1 times t. And of course, that just means that this is the natural log of CA over CA0 equals K1 times t. And I can take the exponent and solve for the concentration of Ca with time, right? Then Ca equals Ca0 times the exponent of minus K1 times time, okay? All right, so hopefully that makes sense, okay? Now, let's do the same thing for B. Let's solve this mole balance for B. And if we did that, right, we would know, or we would start with the flow rate of B in minus the flow rate of B out plus RBV is equal to dCB dt, right? And if we do that, well, remember, this is also a constant volume ideal batch reactor. So those go away. And we can do this. We now need an expression for RB. Well, one of the things that we didn't talk about yet was that for a specific reaction, right, where A, let's say, goes to B, this makes a lot of sense. So the rate of A is just equal to minus the rate of reaction for B, right? Because as we consume A, we have to form B. Now, there's a much more general way for us to write this, and that is that for any reaction, the rate of a species over its reaction stoichiometry is equal to a constant. And if you guys can, box this in, highlight it, do whatever you can, because we're going to use this a bunch of times throughout the course of the semester. But for this problem in particular, it gives us RB over the stoichiometry for B equals RA over the stoichiometry for A. And so RB then just equals RA times the stoichiometry for B over the stoichiometry for A. Now, if you remember for Thermo 2, the stoichiometric coefficient for a reactant is negative, and the stoichiometric coefficient for a product is positive. So this is really RA times +1 over -1, or RB equals minus RA. And if we put that into our rate law, well, that means that dCB dt is equal to minus K1 times CA times V. So our expression then for the change in the concentration of B over time, or sorry, I actually jumped the gun just a little bit, right? This is NB, and that is NB. I apologize for that. So dNB dt is equal to K1 times Ca times the volume. And to solve this, again, we have concentrations here and moles, which we can't do, but we know that this is at constant volume. So I can divide both sides by volume again and get that the change in the concentration of B with time is K1 times Ca. Well, this is actually quite helpful for us because we have a functional form for Ca, right? It's K1 times Ca0 times the exponent of minus K1 times time. And so now, if I want to find an expression for the concentration of B with time, I have to multiply both sides by dt and integrate. So if I do that here, right, this just becomes dCB, and we're going to integrate that from the initial concentration, which was 0, to the concentration of B. That equals K1 times Ca0 times then the integral of the exponent of minus K1 times T dt from 0 to T. And we also know how to take that integral. So remember, in a generic form, right, the integral of the exponent of minus a times t just equals minus 1 over a times the exponent of minus at, right? That's just the law of integration for an exponential. And if we do that, right, and we actually do this integration, we'll find then that CB equals K1 times Ca divided by minus K1 man, I made a mess of that. Ca0 over K1 times the exponent of minus K1 times T from 0 to T. And then if I do this, that means that CB then just equals minus, this just becomes minus Ca0 times the exponent of minus K1 times T. And then minus, if T is at 0, then this just becomes 1. So that just becomes minus a negative Ca0. And if I just simplify this a little bit, then CB equals Ca0 times 1 minus the exponent of negative K1 times time. Okay. And so now I have an expression for the concentration of A with time and the concentration of B with time. And the good thing about that is that I can plot them. And plotting those two, I'll bring up on the right-hand side here. There's the concentration of A and the concentration of B as a function of time, given the rate constant that we assumed. Okay, and the nice thing is that since A goes to B and the volume is constant, you should expect that the concentration of B at the end of the process is equal to the concentration of A at the beginning, and that's exactly what we see here. Okay. Now, another common question that that we're interested in a lot of times when we're doing reactor design is this concept of conversion. And that's given the symbol X. And the conversion of A really is defined as the moles of the reactant that have reacted over the moles of the reactant that were fed to the reactor. Okay. And there's a way for us to think about this that can be a little bit helpful, I think. And if we think about the number of moles of A that have been reacted, right? So that means that, this thing, moles of A reacted, equals the moles fed times the conversion, okay? And if that's true, right, this is just equal to NA times X, right? Or times the conversion of A. And so if we want to try to figure out the moles of A that are remaining in the reactor at any given time, well, that's simply, right, the moles of A that are left in the reactor really is just the moles of A that were fed minus the moles of A reacted. And so that is Na minus Na, or Na0, times Na0 times X, right? And so we actually can always know the constant, or the moles of A, from the initial number of moles times 1 minus the conversion. We also can use this to help us mathematically. So sometimes, instead of wanting to know how the concentration changes with time, we design reactors a lot around this concept of conversion. And if that's true, we might also, just like you see on the right-hand side, want to figure out a way to represent the conversion as a function of time, not just the concentration or the number of moles. And to do that, let's start in the same place that we did for the mole balance, right? We ended up with dNA dt was equal to minus K1 times Ca times volume. Well, Ca times volume is also just Na, right? So that's just minus K1 times Na. So let's make this substitution into both sides of this. So d Na0 times 1 minus Xa dt equals minus K1 times Na0 times 1 minus our conversion here. And this here is just Na0 minus Na0 times Xa. So if I take this derivative, that's just minus Na0 times dx dt equals minus K1 times Na0 times 1 minus x. And this integral, we should divide both sides by minus Na0 and get dxa dt equals K1 times 1 minus x. And to integrate this, we have to get the conversion onto the left side. So we have dxa over 1 minus xa is equal to K1 dt. And our bounds for our integration are 0 to time. And at time equal to 0, the conversion is also 0, right? So 0 to t and 0 to x. And if we solve this, right, we're going to have another natural log function and then take the exponential. You'll find that xa equals 1 minus the exponent of minus K1 times t. And so as we move in time in the reactor, the conversion gets closer and closer and closer to 1. Okay, does that make sense to everybody?
I had a question, more just me being really type A, but they gave us numbers. Was our goal of that to just derive equations, or were we looking for specific values with those numbers?
So these values that are here on the right-hand side that I plotted are using the values that you were given, or that are given in the example problem.
Okay, so you plotted them because they're all functions and not like, here's an answer.
Yeah, that's right. Because, and that's a really good point. So you could have been asked, well, how much time does it take to reach a conversion of blank? And then you could have either read that off the plot or used the equations that we derived to find that. Yeah, that's a really good question. And that's something that you're going to see happens a lot throughout the course of the semester, is that, once you, at least I've always thought of it this way, is that once you have the equations and plot this, you can pluck off the concentration or the conversion anywhere you want. And so I generally tend to use the real numbers that are given and just do a lot of just plotting as a function of time. Actually, directly addressing the question that was asked, the next slide was determine the amount of time that was required to reach a conversion of 0.1. So here, right, we have this equation. We can just rearrange this to find that the time is equal to the natural log of 1 minus xa over minus k1. And so, in this problem, we are, right, that's just the natural log of 1 minus 0.61 over, or 61% conversion, over minus 0.1. And remember, the units were seconds to the minus 1. And so this is like 1 over seconds. So seconds comes onto the numerator. And so we can find that the time is equal to 9.4 seconds. So that was a very timely question. And yeah, so this is one way that we could just use the equations that we just derived. So that was good. All right, the second example that we're going to solve here is a little bit more difficult. It doesn't maybe necessarily look like it on the surface, right? We still have a batch reactor. We still have one reaction that is occurring, except now that reaction is A plus 2B goes to C. And we're given the reaction rate constant. You will notice that when you have a multi-reactant reaction, that the units on the reaction rate constants, the reaction rate constant, are a little bit more complicated. We're given the reactor volume, we're given the initial concentrations of A and B, and we're asked in this problem to determine the concentration of A, B, and C and the conversion as a function of time. And this is going to be more complicated because of our rate expression. And I think that's the first thing to do, is let's think about what is the rate law for A here. So does anybody who's still with us want to give this a shot? If we assume that this was an elementary reaction, what would the rate law be?
Would it be minus K CA CB squared?
Exactly. Okay. So now we have minus K1 times CA times CB squared. Now, this is why the units for K have to be so much more complicated. So if you see from this problem, the units are liter squared per mole squared times 1 over seconds. And then we're going to multiply this by, Ca, which is moles per liter, times moles squared per liter squared for Cb squared. And so these end up canceling. And you end up, if you remember, we're at dNA dt is equal to minus RA times the volume. So you have to get to a point where you're at moles per time. And so the units for K1 facilitate that. So then after here, we multiply by volume, we get back to moles per second, just like you would hope to there. All right, so let's look at this for a second, where we have minus K1 times Ca times Cb squared going into this rate expression. Well, that means that we have dNA dt equals minus K1 times CA times CB squared times the volume. If we assume that our volume is equal to a constant, we end up with dCA. I guess there's a couple of ways to do this, but you could get that dCA dt is equal to minus K1 times CA times CB squared, right? And we know that at t equal to 0, CA0 equals 0.75, right? So why can't we just solve this equation? Why can't we just integrate it? Anybody? What else is changing here?
CB?
Yeah, that's right. So CB is also changing. So now we have to do the exact same thing for CB. So let's just put a box around this, right? This is going to be one of our equations. Well, remember, we just talked a moment ago that RA over the stoichiometry for A has to be equal to RB over the stoichiometry of B, which has to equal RC over the stoichiometry for C. So here, right, that means RA over minus 1 equals RB over minus 2. So we know that RB is equal to 2 times RA, right? We could have known that just by looking at the equation. But if we do the exact same thing, well, we know that then dCB dt then equals minus 2 times K1 times CA times CB squared. And at t equal to 0, CB0 equals 2.0. And we also can do the same thing for C. And if we do that, we know that RA over minus 1 equals RC over 1, or that RC equals minus RA. And find that the concentration of C as a function of time, or the change in the concentration of C over time, is just K1 times CA times CB squared. And we know that at t equal to 0, CC0 is equal to 0, right? Okay, so we have these three equations, but they're all coupled ordinary differential equations, right? How do we solve coupled ordinary differential equations analytically? Anybody? This is where being in person in class is much more entertaining, because people are all looking at each other like, I don't know, right? Does anybody know, or does everybody not know? So just jump in with a thought, even if you don't know.
I do not know.
Okay, great. Honesty, I like that. Anybody else not know?
I don't know either.
There we go. Great. This is good. You know why you don't know? Because you almost can never do it. It's so rare to be able to solve coupled ordinary differential equations analytically. And this is not one of those situations. So if we can't solve them analytically, how are we going to do it?
Do you put it in a computer program?
Exactly. We have to use a computer program. Now, some people prefer to do this in MATLAB or Polymath or some other program. I don't want to make everyone learn one specific program. And in fact, when you go out into your real life, the numerical program that you're going to use the most often is Excel. And we can do this in Excel, okay? And we can do this using Euler's method, okay? Which may or may not ring a bell to you guys. But I'm going to show you the principles on how we can solve this in Euler's method now. And then you're going to have some practice doing it on the homework, and we're going to do it a bunch of times throughout the course of this semester. So by the end of this semester, you will be Euler's method and Excel experts, I guarantee it, okay? And Euler's method works in a very, very straightforward way, all right? Basically, what we're going to do is we're going to take this derivative, okay? dCA dt equals minus K1 times CA times CB squared. And the thing that you are used to doing in calculus is saying that, you know, if we had delta CA over delta T, right, as delta T goes to 0, it becomes dCA dt, right? You're used to kind of like thinking about the calculus in going from real changes to infinitesimally small changes. Well, we're going to do the opposite here. Euler's method is really interested in what is the size that we can jump where the differential still matters, right? Or that we're not breaking any crazy rules, right? And so here's what we're going to do. We're going to replace dCA with delta CA over delta T equals minus K1 times CA times CB squared, okay? Now, if we do this, what we can say is that any instant, the change in the concentration of A is equal to minus K1 times CB times, or sorry, CA times CB squared times delta T. And here's the great thing, is that, you know, this is the change in the concentration over our time. CA, it's like making a prediction. So CA is the concentration of CA now. CB is the concentration of B now. And delta T is our time step. And the great thing is that we get to choose this. And as long as the time step isn't too large, we didn't break any rules here in terms of our differential. So I know that this isn't going to be very comfortable for you guys right now. But like I said, we're going to practice this on the homework and in class several times. So what we're able to get from here, so we're taking these jumps in time, right? We're going to go from t equals 0 to t equal to, you know, whatever delta t is. Then the next time step is 2 times delta t, etc. So what we're able to do is we're going to calculate the change in the concentration over delta CA. So at t equals 0, let's kind of make a table out of this. So at t equal to 0, that's just CA 0, okay? And after the first time step, right? So CA, we'll call it not 0, but CA1, right, at t equal delta t is really just equal to the value that it just was, right, minus K1 times CA0 squared times CB0 squared times the time step that we took. And CA2 is going to be equal to just CA1 minus K1 times CA1 squared times CB1 squared times the time step. And we're just going to do this over and over and over again for for our process. So we have a method here to do this for A. We need to do the same thing for B, right? Because B is going to change as well. And we're going to apply Euler's method there. So if we look at the differential for B, right? Remember dCB dt was equal to -2 times K1 CA times CB squared. Well, doing the same thing we just did, delta CB equals 2 times K1 times CA times CB squared times delta T. And if we did the same thing, right, CB1 would just be CB0, and sorry, that's minus 2 times K1 times CA, 0 times CB0 squared delta T, and so on. And we'll do the same thing with C, and you just get that delta CC equals K1 times CA times CB squared times delta T. Doing the exact same method over and over and over again. So the trick here is going to be how you set up the Excel file, okay? That is a great question, okay? How do you set up to do this in Excel? It is extremely easy to do. It's going to feel weird the first couple of times, but it's very easy to do. And I want to talk about this in office hours. So please come. I am extremely happy to help you guys to solve this problem in Excel, or to show you how to implement Euler's method in Excel. Okay, it's something that you'll have to do throughout the course of the semester. So if you do that, you get the concentration of A, the concentration of B and C, and conversion as a function of time. So we're able to do all of those things. And you just end up with an Excel file that has, but depending on the time step, will dictate the number of rows, right? So the total time and the time step is gonna do that. And you guys actually will have a homework problem in homework 1 where you don't even solve a problem in the context of concentrations and times. But I ask you guys to play with the time step, because remember, if the time step is way too big, you're going to end up with nonsense answers, because the deltas that you calculate are going to be enormous. If the delta time that you choose is too small, you're just going to end up with a massive, massive Excel file. In fact, the first time that I started solving the problems this way, I was doing this. I had very, very small changes in the time. And when I did that, I had 10,000 row Excel files, until I thought, listen, this is insanity. There's no way that the time step has to be this small. I don't need 10,000 steps. And as a general rule of thumb, now I try 100 steps first. So I know the total time, and then I try 100 steps and see what happens. And in the homework problem that you guys will have, you'll get to actually compare the accuracy of the correct analytical solution, because I gave a problem with an analytical solution versus one that has the numerical answer that you guys are going to come up with at the different steps. Okay. All right. Does anybody have questions about this?
I had a question about the equations you put in the table,
Sure.
which I just wanted to make sure I was understanding the algebra of the different equations. So in CA1, you have CA naught squared. And I wasn't sure if that was because you were multiplying CA naught through.
No, thank you. That's just me making a stupid mistake. So
Okay.
thank you.
No, thank you for addressing. I just wanted to make sure I knew the math, but.
Yeah, you're good. That was my fault. I'm sorry about that. Yeah, great question. All right. So the last thing that I want to talk about with this problem is also about the time element. So, here I plot it over 5,000 seconds. But if you look at this, the real action doesn't happen between 1,000 and 5,000 seconds. So you guys are going to be asked to plot a lot of things during the course of the semester. And let's say that we had plotted from 0 to 27,000 seconds. It would be nonsense. And even to 5,000 seconds doesn't really give us a lot. So one of the things I want to ask you guys to do is, as you're working through problems, let's focus on time ranges where you're not getting, a conversion equal to 1 or concentrations leveling off forever. You're really, really interested in the dynamics. And that's all that I did here in this problem, is say, well, the time here is way too long to really understand what's going on, and actually to even compare with different changes in the time, right? If you wanted to change delta t from 1 second to 10 seconds, how would you know whether you got it right? They might all just look, or whether it's accurate enough, they all might just look flat to you. So be mindful of that as you're solving some of these problems if you can, okay? All right, the last thing I want to do today is really a bonus for YouTube example. And I like this example because it makes it look like it's far more complicated than the first example that we solved in this lecture. And we're talking now not about liquid phase reactants, which, or it may have felt obvious to you guys during the course of that problem, but we're talking about gas phase reactions. And we're asked to consider a gas phase reaction where A goes to 2B in an ideal batch reactor. And the reaction proceeds in a flexible vessel such that the reaction volume is allowed to change, but the pressure is constant. So now not only are we really specifically saying that it's a gas phase reaction, but the number of moles go up. So we know that in a gas phase, right, we're sort of bound, let's say, by an equation of state. And the easiest one for us to consider, of course, is the ideal gas law, where the pressure times the volume is equal to the total number of moles, right, which is actually the sum of Na plus Nb times RT, right? And if we're looking at this particular system, well, if we were operating at constant volume, right, the pressure would obviously have to go up in this reaction because A goes to 2B. We're going to be making more moles of B than we started with A. So this is almost like a decomposition of A goes to 2B. Instead here, what we're doing is we're going to keep the pressure constant, and we're going to allow the volume of our batch reactor to change. It could be a piston cylinder. It could be a bellows, like a flexible plastic, like rubber material. Any number of things could happen. Now, what does that mean for our mole balance for a batch reactor? It doesn't change, right? Because it's still in minus out, plus generation minus consumption is accumulation. So we still have dNA dt is equal to Ri times V. Now, in our process here, right, we know A goes to 2B. It's an irreversible reaction. So we also know that dNA dt is equal to then minus K times Ca times the volume, okay? So now what we really need to be able to do is to come up with an expression that we can integrate. And how is it that we feel comfortable dealing with this change in the volume? And there are a couple of ways, quite frankly, that you can do this. So one of those ways is to recognize that Na is just Ca times V. And so you could do this, dCAV dt equals minus K1 times Ca times the volume. And if I differentiate this, then I know that this means that Ca times dV dt plus V times dCA dt equals minus K1 times Ca times the volume. Okay, I mean, this is not so bad, but it turns out that for liquids, this is the form that we want, because when a liquid reactor changes volume, it's because we're feeding at a known flow rate. So we're going to know what dV dt is all of the time. Now, for a gas phase reaction, it turns out that the math for this becomes very, very complicated, and it becomes simple at the end. So I'm a good advocate for this approach with liquids, because this is going to be a constant, essentially, and then we'll be able to solve this problem. But for a gas phase reaction, I want to implement this in a way that is a little bit easier for us to understand, and it's not by introducing the concentration. Okay, that makes this, for this problem in a gas phase reaction, very, very complicated. Okay, so I don't want to do that. So we won't. Okay, this is something we're going to revisit when we get to liquids, but it is a natural thing to want to do. So I wanted to make sure that you guys saw it, and we will sort of circle back to that later on in the semester. Sometimes it is much easier for us, even if we want to know the concentration, to calculate the moles and then just divide by the volume, whatever it happens to be. And that's what we're going to do here. We're going to kind of take advantage of the fact that the pressure would be constant, and we know what the pressure is, to always have the ability to calculate the volume as long as we know the number of moles. So instead of making this substitution, here's what we're going to do. We're going to find an expression for the concentration of A in terms of moles and volume. Well, we already know that Ca is just Na over V, right? And we know from the ideal gas law what the volume is equal to, right? The volume is Na plus Nb times RT divided by the pressure. So this becomes Na divided by Na plus Nb times RT, and then this is times the pressure, okay? So before we do anything, right, is this okay with everybody?
Yes.
Okay, great. So now when we do this, right, we know that dNA dt then equals minus K1 times Na over V times V. And V at any point we also can find, right? So we know that this is just times Na over V, or sorry, Na, I apologize, times the pressure times Na plus Nb times RT times the volume at that moment. And we know what that is. We just found it, right? So the volume is still just Na plus Nb times RT over P, right? In brackets. And it doesn't always work out this cleanly, but it turns out that because this is first order, all of that goes away. All of it. If it were a second order reaction, we'd still have some fragments left, and the math would be a little bit more difficult. But for a first order reaction, this is very simple. And this just becomes dNA dt equals minus K1 times Na. And that's great. We already solved this problem previously, except it was in terms of the concentration, right? This is just a first order ordinary differential equation. So if we have an initial condition, right, that at t equal to 0, Na is equal to Na0, well, fine, then we know this is dNA over Na integrated from Na0 to Na equals the integral from 0 to t of minus K1 dt. And if we solve that, right, we know that Na is just equal to Na0 times the exponent of minus K1 times time. And that's the math that we just did a moment ago. And it's very, very similar for B, right? So we know that Ra over the stoichiometry for A is equal to Rb over the stoichiometry for B. So that means that RA over -1 equals RB over -2. And so that means that RB is equal to 2 times RA. And we can do the exact same substitution in our mole balance, is that dNB dt equals 2 times K1 times Na, which is 2 times Na0 times the exponent of minus K1 times T. And again, this is the exact same math that we just did a minute ago for example 1 in terms of the concentration. So to solve this, right, we have dNB integrated from NB0 to NB is equal to 2 times Na0 times the integral from 0 to T of the exponent of minus K1 times T. Oops, sorry, I got a little ahead of myself there. Of minus K1 times T dt. And if we do this integration as well, just like we did a second ago, and I apologize, 2 times K1 times Na0. If we integrate that, we also find that NB equals 2 times Na0 times 1 minus the exponent of minus K1 times T, right? And so now we have NB and Na in a very straightforward way as a function of time. And those can be plotted, right? So we have the exact solution here as a function of time. So we have the concentrations, and here, let me make this bigger so you guys can see it. So you have the concentration of A and B with time, and I calculated the initial concentration of A, right? You can find Na0 from the equation that we wrote here, right? That, you know, Na0 is actually, given the information that we have in the problem, just to show you guys, right? So we have the pressure, the temperature, and the volume. So we can actually calculate the number of moles of A. And if it's all A at the beginning, then, you know, Na0 is just PV divided by RT, right? And we have the volume, we have the pressure, we have the temperature, and the ideal gas constant doesn't change, right? So that's P0 or P times V0 over R times T. Okay, so we were able to calculate that relatively easily. So this is great. So we have Na0 or Na and Nb as a function of time. I also explicitly then found the volume, because now that I have the number of moles at any given time, I could also just apply this equation to find the concentration, right? Because I have Na as a function of time and Nb as a function of time. So I can find the concentrations using that equation. Also, because I know the number of moles of A versus time, we can use the conversion equation that we had to find conversion. We also can find the volume as a function of time because we have our equation for volume. So hopefully, you know, this sort of bonus example shows how a problem that appears to be very complicated at the beginning, it looks a lot more difficult than the first example, but it really is not. It's just a matter of choosing the right mathematical pathway to solve it.
I had a quick one about, for example, 2, when you had 2 reactants.
Yeah.
Is like the conversion there, like of both, like moles of A and B?
Oh, that's a great question. So in that example, here, let's just go to that really quick. In this example, conversion, you would seem to think is sort of a convoluted thing, but you would use conversion based on the limiting reactant. So here, A is the limiting reactant. So if you consumed all of A, right, you would only consume 1.5 molar of B. So you would still have some left over, and you actually can see that here in the solution. So that's a really good question. Here, we've defined conversion as the conversion of A, even though it's not explicitly written here. Great question.
Okay.
Now, that's very, very common. If for some reason B was the molecule of interest, that, you were really, if for some reason B was somehow limiting the performance of the cell, you could also use B under that circumstance, but it's really not common. So usually you will use the limiting reactant as the species for conversion.
Okay. So those formulas from example 1 that we derived, are those still valid then?
Yeah, absolutely. And so in this example, we had defined the conversion of A. I'm trying not to give anybody whiplash here, as the moles of A reacted divided by the moles of A fed to the reactor. And that is exactly the same definition here. Now, in our spreadsheet, for example, in our Excel sheet for the second example, right, we have NA as a function of time, right? We have it at each of these discrete time elements. So really what you can do is if you want to calculate the conversion of A with respect to time, right, that's the moles of A reacted minus the moles of A that have been fed. So this is really like N, if you think about the moles of A reacted, this is like Na0 minus Na as a function of time, right?
Right.
So this is what we had, this is what's left. So what is, the difference between those is the moles of A reacted divided by the moles of A fed. And so that equation you could definitely use to calculate the conversion as a function of time.